So in this class we will prove Jensen's formula and Hadamard's theorem. So the consequence of these results will be discussed later. So Jensen's formula relates the modulus of a function on a circle and the moduli of the zeros of fz. So of course we are considering analytic functions. So let us go to the statement. So you start from an analytic function in a domain containing the closed disk of radius rho, and we assume that it is non-identically zero. So there are only finitely many zeros inside this disk. Now to make it easier, we assume that f of 0 not equal to 0. Okay, so here we denote a1, a2, etc., a and b the finitely many zeros of fz in this inside this disk. Now this formula tells you that log mod f of 0, because it's a real logarithm, is equal to the minus of summation I equal to 1 to n log rho by mod ai. Here ai's are the zeros counting up to multiplicity inside the disk of radius rho, plus 1 by 2 pi into this integral. So this is the formula. So let us prove it very easily. The major ingredient is the Poisson integral formula for a harmonic function. So what you do first you consider capital Fz defined in this way. Then you will obtain that this Fz is analytic, obviously, because we are taking the product. It's a finite product, and the only possible singularities are ai's, but that will get cancelled because they are zeros of fz. So using the factorization, that will cancel. So and you will see that this capital Fz will not have any zeros inside the disk of radius rho. Now since it is not equal to 0 for any z, you look at the branch of logarithm log fz inside this disk mod z less than or equal to r. So its real part, so this is an analytic function now, so its real part is log mod fz, it is harmonic. Now for any harmonic function we can apply the Poisson formula, which was discussed in the previous semester. So if you want to recall, you can refer the page 168 of textbook Alphonse. So this is the formula. So if you apply that for log mod fz, you will get in fact it is applicable for any a inside the disk, strictly inside the open disk. So we apply it for a equal to 0. So log mod capital F0 will obtain this. A simple computation will give you this. Now f of 0 is this, and if you apply log, you will get the required identity. So this is Jensen's formula. Now there is a modified form of Jensen formula, which is known as Poisson-Jensen's formula, which gives you a formula for log mod fz for any z inside this disk of radius rho. So there we apply the general Poisson formula, that's all. I mean, here we applied the Poisson formula for a equal to 0, but there you apply it for general formula. So you will obtain the same thing. I mean, the same proof, imitate the same proof, you will get the Poisson-Jensen formula. So I described everything here. Now the major task is to obtain the Hadamard's theorem. So before that, let me recall some notions here. So recall the notion of genus of an entire function. If fz has a representation of this form, we call where this is the small, here h is the smallest integer. So h is the genus of this sequence, I mean this canonical product. That means the smallest integer with this property. I mean this summation is finite. And if gz is a polynomial, then we say that fz is of finite genus, and that genus is a maximum of these two quantities, degree of gz and h. So this is the definition which we had. In fact, we will find an equivalent definition here that follows from this lemma. So this lemma tells you that if fz is an entire function of finite genus, and you assume that f of 0 is not equal to 0, then you have this representation e raised to gz into the same thing. But here the thing is that this h is the genus. I mean this h is equal to genus of fz. So for that you need, in this representation, gz should be a polynomial of degree less than or equal to h. So the idea is that one side is trivial. If you have such a representation like this, then you know that maximum of the degree of this polynomial and this h is the genus. So if you have such a representation, then by definition itself genus is h itself, and degree of this is less than or equal to h, and so. So what happens if you in the general case, how do you obtain such a representation? That's the question. So you assume that k equal to degree of, so in general also, if fz is a finite genus, then you will get such a representation, but you don't know whether the degree of gz is less than or equal to h. That need not be true in general. So degree of gz is, if it is greater than h, then that will be the genus of fz. So suppose you have such a representation, that means degree of gz we denoted by k, which is strictly greater than h. Then what we do, we just make a small change here. So what you do here is, so since k greater than h, this infinite product will converge with h replaced by k. So you can go up to k, because h is the smallest integer for which this convergence happens. So you add more terms here, correspondingly there will be change here, so you will obtain some g tilde z. So it will be a polynomial. Now what happens is that you can compare with this and obtain that degree of g tilde z will be less than or equal to degree of gz, that is equal to k. So that is easy to obtain, because you are adding some terms here, more terms here. So definitely the only possibility is that the terms in gz may be absorbed here sometimes, but however it will not grow, the degree will not grow beyond the degree of gz. So that's what we obtained here. So with this lemma, we can go to a remark. So we can accept this as a definition of genus of fz if f of 0 not equal to 0. That means the smallest h such that fz has this representation with the degree of gz is less than or equal to h. Now we are going to the definition of order of an entire function. You define m of r to be the maximum of mod fz on mod z equal to r, the circle is a compact set, so this is a continuous function, so maximum axis. Now by order, what you define it in a heuristic way like this. It is a limit supremum of log mr by log r as r tends to infinity. In fact, to understand it in a better way, you can see that it is so by this lemma, the order lambda of fz is the smallest number such that mr less than or equal to e raised to r power lambda plus epsilon for every epsilon greater than 0. So for sufficiently large r. So this is something which characterizes the order. So this definition will not give you what is order, but this will give you something which you can use. So this is easy to prove. By definition, lambda is the order of fz, means this quantity will be less than or equal to lambda plus epsilon. For every epsilon, lambda plus epsilon will be an upper bound for this for large r, because limit supremum is lambda. So lambda plus epsilon will be a bound for this. Now you do this simple computation, you will obtain that mr less than or equal to this. And the converse also, you will have the means by a reverse computation you will get the converse also. So this is something which we will use. So it is the smallest lambda for which this happens, mr less than or equal to e raised to r power lambda plus epsilon. Now we are going to the big business. I mean, we have to prove the Hadamard's theorem. So I will explain the details of Hadamard's theorem, I mean the consequences and its importance later. So here I will just prove Hadamard's theorem. It tells you that if you fz is an entire function with f of 0 not equal to 0, then if h denotes the genus of fz and lambda denotes the order of fz, then they satisfy this inequality. H less than or equal to lambda less than or equal to h plus 1. The proof is a bit tricky. So first we observe that order of fg less than or equal to maximum of order of f comma order of g. That is easy. Simple observation that if you denote m1 is the supremum of f and m2 is the supremum of g, then m1 are less than or equal, and lambda 1 and lambda 2 are the orders of f and g respectively. Then it will satisfy these inequalities, and that will give you m1 to m2 satisfy this inequality. And from this you will obtain that if you replace by maximum of lambda 1 and lambda 2 by the maximum, then a simple observation will give you that m1, the supremum of fg, is bounded by e raised to r power k here it is power lambda plus epsilon plus something like this, okay, log 2 by log r. Therefore the MR satisfy the inequality that e raised to r power lambda plus something, okay, for all epsilon greater than 0 for large r. So therefore the order should be less than or equal to lambda. That's what we have, because order should be the smallest number with the property that it is less than or equal to lambda plus epsilon. So that proves the claim. So that is something we will use, because your f has a representation in a product form. So we will see that the order of f is bounded by cannot exceed both of the quantity e raised to gz and that product. So but what about e raised to gz? So gz is a polynomial of degree less than or equal to h. So the order of e raised to gz will be bounded by h. That is easy to prove, because you will get that absolute value of e raised to gz is bounded by this, and if you compute the supremum over mod z equal to r, it is bounded by this quantity. Now log mr will be bounded by this quantity, log mr will be bounded by this quantity. Here you take r raised to k outside, since ck not equal to 0, you will have this. Now you can see that as r tends to infinity, these quantities will vanish, I mean they are negligible. So what is remaining is log rk plus log mod ck, or something which is negligible, divided by log r. So what happens, this is k log r. So if you divide by log r, it is k only. Here you will have k. Here this quantity will converge to log mod ck, but it is divided by log r, and r tends to infinity, that will go to 0. So what is remaining is k. So this quantity is bounded by k. So that means e raised to gz has order bounded by, if gz is of degree k, then it is e raised to gz has order bounded by k. So that's what we use here. So order of e raised to gz is bounded by h. Now we will prove that in fact fz is actually the product of two quantities, fz into e raised to gz into the product, that canonical product. So we will prove that the canonical product has order less than or equal to h plus 1. So already this has product less than or equal to h. So the maximum is bounded by h plus 1. So you will get that the order is bounded by h plus 1. That is the first proof. So we denote pz, the canonical product, divided by pz. So we will prove that its order is bounded by h plus 1. For that we use this notation. EHU is this function with the convention that E0u is 1 minus u, and then pz is actually infinite product EH of z by n. Now first we show that log mod EHU is bounded by 2h plus 1 into mod u power h plus 1. So in fact this is proved by induction, but before that we need to obtain this. For mod u less than 1 we use the series expression for 1 minus u, and this gets cancelled, and you will obtain this quantity is bounded by this infinite series. Now everywhere you replace by h plus 1 by h plus 1, so you will obtain this, and use the geometric series here, geometric ratio here. So it is equal to this quantity. So this is bounded by this quantity. Therefore log mod EHU is bounded by this quantity for mod u less than 1. So mod u less than 1 you have this inequality. Now for arbitrary, so for arbitrary u, what happens, again log mod EHU is the real part of this, and you do this computation, simple computation, you will obtain that log EH minus 1 plus mod u power h, you will obtain this. Now that gives you this inequality, log mod EHU bounded by log mod EH minus 1 u plus mod u power h. This is our second inequality which we will use. Now, so this is something we want to prove by induction. So for h equal to 0, this is straightforward. That is something changed. We assume it for h minus 1. That means you have this h minus 1. You have this. So now for 2 and 3, log mod EHU by, so 2 is this. So you apply this here. Now for this, by induction assumption, this is bounded by this, and you will obtain this. Now for mod u greater than or equal to 1, this quantity is bounded by this. I mean you can multiply by mod u and add them, and you will obtain this inequality very easily. Now if mod u less than 1, we will use the previous inequality which we obtained, and we club them together. So for mod u less than 1, you have this inequality already. So we work on that, and you apply the induction hypothesis, and we apply the inequality 2 and then induction hypothesis, and this simple inequalities will give you this. So hence we complete the claim by induction hypothesis. Now we consider log mod pz. Log mod pz is by our notation, it is summation log. See, mod pz is product, infinite product with eh of z by n. So log of that will be infinite sum with log this quantity. Now we apply the inequality we obtained here. So it is replaced by this. So 2h plus 1 and mod z power h plus 1 is independent of the sum. So what is remaining is this. But this is finite because h is the genus of the canonical product. So this is finite. So what happens that therefore the maximum, so if you compute the MR here, so MR will be bounded by the maximum of this into something. I mean, this quantity you denote by some alpha. This quantity is finite. So that will be bounded by r raised to h plus 1. So on mod z equal to r, this is mod z, this is r raised to h plus 1. So that is bounded by. So log MR is bounded by this quantity. So therefore, if you divide by log r, this is h plus 1 plus something, some constant by log r. So that this quantity will go to 0. So remaining will be h plus 1. So order of pz will be bounded by h plus 1. That's what we proved. So hence we proved the one inequality lambda less than or equal to h plus 1, because we already proved that e raised to gz has order less than or equal to h, and the other part, the product, has order less than or equal to h plus 1. So the maximum is less than or equal to h plus 1, and that will be the I mean, we know that the product of two functions. The first claim we prove that the product has order less than or equal to the maximum of each term. So lambda is less than or equal to h plus 1. Now we need to obtain the other inequality. Here we use Jensen's formula. Now you start from, suppose h is the largest integer less than or equal to lambda. So lambda need not be an integer. So you start from the largest integer less than or equal to lambda. So then we will have h plus 1 is strictly greater than lambda, because if h plus 1 equal to lambda, then this will be satisfied by h plus 1. So we will have strict inequality here. Now we prove that summation h equal to 1 to infinity 1 by mod an power h plus 1 is finite. So this is something we will prove here. So new row denote the number of zeros n with the mod an less than or equal to. So by Jensen's formula, we apply Jensen formula with row replaced by 2 row. So you will obtain this identity. And here in this sum, since we are applying it for 2 row, there will be more terms. I mean, all the zeros will come inside the disk of radius 2 row. But if you remove those with mod ai greater than or equal to row, then you will get an inequality. So that inequality is written here. So we will obtain, repeating this, you will get this inequality, and finally, you will obtain this new row into log 2 less than bounded by this integral minus log mod f0. So here we do a simple technique. So f of this on mod z equal to r is bounded by m of 2r, because mod z is equal to 2 row here. So here this is bounded by m of 2 row. So the whole thing quantity is bounded by log m of 2r, and the remaining integral is 2 pi by 2 pi, that gets cancelled. So what happens that new row divided by this row power lambda plus epsilon is bounded by 1 by log 2 into this quantity by this and this quantity by this for all epsilon greater than 0. Now we recall that lambda is the order. So lambda is the smallest number satisfying m of r less than or equal to e power r power lambda plus epsilon for every epsilon greater than 0. Since it is satisfied by every epsilon greater than 0, for this epsilon you take epsilon by 2 here. Okay, so for epsilon by 2 also this will be satisfied for large r. So the stage will be different. That's the only difference. So you will get that this quantity is bounded by this quantity. So this you can m of 2r 2 row is bounded by e raised to 2 row power lambda plus epsilon by 2 there. So log of that will be bounded by this quantity. So here you have epsilon by 2 and here you will have epsilon. So row term will be in the denominator. denominator, and therefore as lambda tends to rho tends to infinity, this quantity goes to 0. So that means mu rho by rho power lambda plus epsilon goes to 0 as rho tends to infinity for every epsilon goes to 0. So that's what we do here. Now we order the zeros of f set in the increasing of absolute value. So therefore nu of mod an means all the zeros less than or equal to mod an. That means that will be bounded below by n because of this ordering. So therefore we have nu of an by mod an power lambda plus epsilon goes to 0 as n tends to infinity. We just proved it now. So after some stage. So after some stage this quantity will be less than 1. So what happens from this inequality, we have n less than or equal to this less than or equal to this quantity. So this is one inequality which we will use. Now this implies that mod an power minus h, that means 1 by mod an power h plus 1. So a simple computation, this is bounded by this, and therefore this series is bounded by this series, and you can choose epsilon with this property because h plus 1 is strictly greater than lambda. Therefore there exists an epsilon such that h plus 1 is strictly greater than lambda plus epsilon. So this will be greater than 1, therefore this series will be convergent, therefore this series will be convergent, and we proved that this summation is fine. So hence we obtained that f set has a representation of this form, e raised to g z into this infinite product. Here this infinite product represents the canonical product because we have already proved that summation 1 by mod an power h plus 1 is finite. Therefore this representation will hold for f set. But the only problem is that we don't know what is this. This, for the time being, we know only that gz will be an entire function. So if you are able to prove that this is a polynomial of degree less than or equal to h, then by definition we had earlier, this h will be the genus of f set. Therefore, we chose h to be the largest integer less than or equal to lambda. So if we prove that largest integer is the genus, then we obtain that genus is less than or equal to lambda, the order, and the other inequality we already proved, lambda less than or equal to h plus 1. So the only task remaining with us is to prove that in this representation this gz is a polynomial of degree less than or equal to h. For this we consider the Poisson Jensen's formula. Let me recall that log mod f z equal to this. And we apply the operator dou by dou x minus I into dou by dou y both sides. Remember, log f set is log mod f set plus I into arg f set. So this is the real part of log f set. So you write it as u plus iv. So if you have u plus iv for anything, so dou by dou x minus I dou by dou y of this u, that's what we are computing. This is a u. So that is dou u by dou x minus I dou u by dou y. But the Cauchy-Riemann equation, that is dou u by dou x plus I dou v by dou y, where u plus iv is our function under consideration. This is by Cauchy-Riemann equation. Here u plus iv is log f set. But remember that this actually represents the d by dz of f set. That means whatever function we have. So this is the derivative of our function u plus iv, which is log f set. So this represents d by dz of log f set. That means f dash z by f set. So left hand side becomes f dash z by f set. So similar computation you do at the right hand side. So again you will have the same arguments, and finally we will end up with the right hand side will be summation I equal to 1 to n. In fact this will be up to new row because we are considering mod ai less than or equal to r in that Poisson Jensen formula. So you will have this representation. So and we do the same thing for the last integral also, and we end up with this computation. I mean f dash z by f set is equal to summation I equal to 1 to new row, this two sums, and then this integral. So that's what we have. Now what we do, we compute the xth derivative of this. Xth derivative of this is derivative you do component wise. I mean each term by term you do the xth derivative by simple arguments. The derivative is minus 1 by z minus a square and so on. So you do it h times, you will have a factorial, a minus h factorial into this. Here also you will have the same thing. Now in the integral you do the h times. Here already a square is there, therefore it will be h plus 2, and there is h plus 1. So this is a straight computation. We will obtain this. Now what we do is we will prove that as rho tends to infinity, the last two terms will go to 0. So as rho tends to infinity, we will end up with only the first term, and rho tends to infinity means this becomes I equal to 1 to infinity. So that's our idea. So first of all, what we do, we look at the integral. So here you add and subtract with this log mod f, we add and subtract log mod m rho. But that will not create any difference because one term will be this into log m rho term will come. So that means this is the additional term which we will have, but you can verify this computation that this integral is actually 0. So this will not create any problem there. So the other term will be this h plus 1 factorial by 2 pi into this term will be here. Okay. Now we do the computation here. If rho is greater than 2 mod z, then you can estimate the denominator also, because rho e raised to I theta will be on the boundary, z will be inside the disk of radius rho by 2. So what happens is that their distance will be at least rho by 2. So that's what we use here. So 1 by that will be less than or equal to 2 by rho. So you apply that here and you obtain this inequality and this integral. So this integral you can directly estimate using this. That is again by Jensen's formula, log mod f0 bounded by this. So this integral you can estimate by this. It's a finite quantity. That's the only thing you need. Okay. So what happens is that all that remaining is this actually. So h plus 1 factor whatever, there is a quantity rho power minus h minus 1 and other terms are finite. So as rho tends to infinity, this goes to 0. So that in that way, in the expression a, the last integral goes to 0. Now we consider the second term. Same computation, rho greater than 2ch. So you will have, this will be bounded by this one, h factorial into 2 power h plus 1. They are all constants. Only two new rho by rho power h plus 1 will be there. So we already proved that this goes to 0 as rho tends to infinity. Hence, as rho tends to infinity, your a gives, the equation a gives dth derivative of f dash z by f z is minus h factorial into I equal to 1 to infinity this. It was up to new rho, as rho tends to infinity, that goes to infinity. So this is what we obtain. Now we consider the expression for fz. It is e raised to gz into a product. That product we denote by pz, the canonical product. So log fz is gz plus this, f dash z by fz. I mean, you take the derivative, that will be p dash by p plus g dash. Now you take the h the derivative. This will be s dh of f dash by f. This will be dh of p dash by p, and this will be h plus 1th derivative of g. Now this already you have an expression, and this you can compute directly. So you compute. Look at pz is a product. So log pz will be the sum, and derivative of that is p dash by p. So that is the sum of derivative of this, and by computation you will obtain that this is this. Okay, so you obtain that, that's straightforward computation. So you obtain that these two quantities are same, therefore s plus 1 the derivative of g is 0. That means g is an entire function which s plus 1 the derivative is 0, therefore g should reduce to a polynomial of degree at most h. So let me stop here. The proof of Hadamard's theorem is a bit lengthy, but we will see some more consequence of these couple of results later.